Using this expression, we can write the integral. We can rewrite this integral to be w is equal to the integral of m vx dx dvx plus vy dvy plus vc dvc. Now the limit of integration have to change from vi to vf, because the variable of the integration now is the velocity. The mass m is a constant, right? So we can take it out of the integral. So we have that this equal to the m, and when you do the integration of the summation, you can separately do the integration of each part and sum it back again when you have the result of the integration. So this equal to the integral of vx dvx. The limit will be the vxi to vxf, because the variable of our integration is vx in this term, and plus vy dvy from vyi to vyf plus the integral of vci to vcf of vc dvc. Okay. Each term of the integration can be evaluated very easily, right? You can see that the integration of the first term is a half of the vx square, and this is a half of the vy square, and this is a half of the vc square. So the result of this integration will be w is equal to the m times half of the vx square from vxi to vxf plus half of the vy square from vyi to vyf plus half of the vc square from vci to vcf. Okay, which is equal to the m/2 of vxf square plus vyf square plus vcf square minus m/2 of vxi square plus vyi square plus VCI square. But you can see that before we have discussed this, that this term is just the VF square, which is the square of the magnitude of the final velocity, and this term also equal to the VI square, which is the square of the magnitude of the initial velocity. So at the end we have that W is equal to the to the half of mVF square minus half of the mVI square, which is equal to the kinetic energy, the final kinetic energy minus the initial kinetic energy, or is equal to the change of the kinetic energy. So we prove the work kinetic energy theorem. The work kinetic energy theorem is an important theorem, and we can use it to solve many problems. Anyway, it has the limit. As we mentioned before, that this theorem applies to the situation that the applied force only change the speed of the object. So we can use the work kinetic energy theorem. But if the force change something else, like the internal structure of the object, we have to be careful when we use the work kinetic energy theorem, because the work done to the object in some parts will change the kinetic energy, but in some part will change the internal structure of the system. So it is not a general principle in the sense that if there is other change in the system occur beside its speed, we cannot use the work kinetic energy theorem directly. We have to be careful on that. Soon we will discuss the conservation of energy, which is more general when we talk about the energy. It is also a pitfall about the meaning of the work kinetic energy theorem. It's about the speed, not the velocity, or at least not directly. Because when we write down the kinetic energy, it is the half of mv square. So this v square is about the speed. There is no direction here, so it's not about the velocity. The work kinetic energy theorem relates work to a change in the speed of a system. Okay, it's a change of the kinetic energy, but the kinetic energy is related to the speed. So it is related to a change in the speed, not a change in its velocity. For example, if an object is in uniform circular motion, its speed is constant, right? The magnitude of the velocity is constant, and there is no work done on the object, even though its velocity is changing all the time, and we have the force act on the object, but the speed is a constant, so the velocity is constant, the kinetic energy is a constant, and there is no work done on the object. This table shows some value of the kinetic energy to the object, that the common object, the kinetic energy of the Earth orbiting the Sun, the Moon orbiting the Earth, the rocket, automobile, and down to the oxygen molecule in air.